Our next speaker is Dr. Mike Joy, who's at the Institute of Governance and Policy Studies at Victoria University. Now, Mike is very well known as a freshwater ecologist, and in his new role at Vic, he gets to be far more involved in policy and systemic issues, which I think is a great use of his skills. I've always greatly admired Mike, not only for his deep knowledge, but his huge and fierce determination to speak out on these issues. And it was only latterly that I think I unlocked a bit of that essence of Mike when I learned that he had left school at 17 and had an awful lot of, and I don't mean this unkindly about academics, real-world experience as a taxi driver, on dairy farms, on sheep farms, as a building labourer, before he actually started university at 33 at Massey. And his master's thesis focused on freshwater fish communities in Tairāwhiti, and then that obviously took him on to his PhD. And I think that being so deeply grounded in the reality of the world out there, and I say I'm not pinging academics in that, I think helps understand why Mike is so terrifically effective and staunch on all these issues. So he is going to talk to us about the biophysical limits to growth, which of course is exactly the relationship we have to get right. So a very warm welcome for Mike, please. Thank you very much indeed.
Kia ora everyone, thank you very much for coming along and for the invite, and thanks to the people here for having us at your marae. I want to, and thank you to Ming for leading us on here and representing us, and I want to acknowledge some amazing people here. It's great to hear Tina, who's sort of been fighting the same fights in different parts of the country and together, but not in the same place often at the same time. I did think when I was invited to come here that it did seem odd to me. It's a bit like, you know, going to teach your mother how to suck eggs, grandmother how to suck eggs, coming to tangata whenua and talking about circular economies. It's like that seems strange. But I'm going to sort of draw out from Tairāwhiti to more of a global picture and trying to, I guess, get us to a bit of humility about what we can do on this planet. I feel we have this huge arrogance of how clever we are, but we've just been users of this amazing legacy of fossil fuels, and we've been able to build this, I'm not talking about this marae, definitely not, but this built infrastructure of the world with our jets and our buildings and we think we're so smart, but it's just this tiny blip of energy that was given to us from the sun over millennia, and we're just blown it in a handful of generations, and now it's coming to end, and I want to talk about some of that reality. Te Mana Te Motu, that's my island in the background there, Mana Island, and my 87-year-old boat that I'm currently the owner of, and go sailing out to that island and other places. And you know, just kind of, to me, it's a message about how the really important things in life don't involve lots of energy. We go to where there's less energy. So I want to talk about some of these things, about the examples from New Zealand of the limits to growth, how we take all that for granted, just introduce this idea of energy slaves and how we're slave drivers and we don't even realise it. We have more slaves than anyone in history, every one of us, and we don't even think about it. About some of the consequences of energy density, just about the reality of future, I guess, and about moving away from fossil fuels and just what that's going to mean. Back in the 70s, an interesting bunch of people put together some models about the future of the world. And they were a really bright young bunch at MIT. The average age was 25, these really smart young people that were given this job of let's see what will happen in the future if we keep sort of along this what is that now being called a progress trap, but to see what would happen in the future. And these bright, optimistic young people built these models and thought that was, going to change the world because they could show what would happen if we didn't change. And of course, nobody listened and they got shot down. But these graphs, the dotted lines are their predictions about a whole bunch of things that are really, really important to us. And all you have to notice is that there's some big inflections in those graphs. But there's a light-coloured part of the line, and I hope you can see, and then a solid part of the line, and then you see the dots. So the light part of the line is going backwards with their model, and then the heavy bit is from when their modelling started in 1970 till now. And those dark lines, the thickest lines, show just how incredibly accurate they were about the future, even though everybody rubbished them at the time, or the economists. But look where those inflections are when everything tips over, is about now, within the next 10 years or so. And we can see this coming. I mean, this is really important stuff. There's very few, I'm a modeller, there's a lot of us that do this kind of thing, but very rarely do we get to see them ground truth like this and just see how accurate they were. Okay, I mean, as a scientist, I know how conservative scientists are. And when 20,000 and it's more like 30,000 now, scientists give a dire warning to humanity that we can't keep going the way we are, that if we don't act soon, there'll be catastrophic biodiversity loss and untold amounts of human misery. This is the reality that we can't, as much as we try, ignore. If we look at New Zealand, then, I'm sure, as Tina said, people are really aware of this now. This is New Zealand. This is moderately or severely polluted rivers in New Zealand. It's pretty much all of lowland, wherever there's intensive agriculture and intensive human settlements. You can see the problems. The little graph on the right here is the number of threatened freshwater native fish species we have just over the last 20, 30 years. It's not an old thing. It's happening now. It's happened in the last few decades. It's happened under the RMA. I'm working on this Canterbury issue at the moment, and all of that damage there, plus a massive amount of water that's been taken and given to a few. Nobody asked. They just took that water and handed it over to those landowners, and now we have this legacy from that. I've done a bunch of work on the economics where we show that if dairy had to pay for its impacts, then it would be a nil-sum game. We would not be doing dairy in New Zealand if it had to pay its impacts. The big part of this impact is nitrogen that we put on the land to grow food. We make our food now, not our food, but the food that we export, we make from oil or fossil fuels, gas in our case, a third off Taranaki, 2/3 from the Middle East. So what's polluting our rivers is completely unsustainable. We have an industry that is completely unsustainable because it's based on fossil fuels. And this latest Environment Aotearoa report is just the nail in the coffin for where we have got to. This is the limits to growth that we've been worrying about for so long, manifesting themselves now. And if you look at it on a global scale, then we have this, we talk about planetary boundaries. This is kind of the latest trendy way to kind of talk about it, and it's really, really important to understand that those big red blowouts there include nitrogen and phosphorus and biodiversity loss and climate change are the things that we know are incredibly important. But I guess if there's a point here, it's that climate change is just one symptom of a complete collapse that we're involved in, and it's going to be the one that's going to hit us, or some of us, hardest. Another point to make, here's another way of that graphic looking at it, but the black dots there in those blowouts are animal agriculture. This is, when you have 98% of the biomass, the weight of mammals on this planet is us and the animals we eat. 2% is wild animals. That's how much we dominate the system and why animals are going to have to come out of our diets if we want to be able to feed the population that we have on the planet. And when you look at New Zealand, I don't know, some people have this idea that we're near the top, we're near the top of environmental performance in the world. We are in the bottom 20th. Out of 179 countries, there's New Zealand, 18th from the bottom of the world rankings on environment. This is including biodiversity, water quality, and marine captures and fertiliser use, we are among the worst in the world. So we've got to, this is a wake-up call. It's just this, we've kind of, the way we've been promoting ourselves on to the rest of the world has been, but we've sort of kid ourselves about that as well. Okay, here's the reality. To meet that 1.5 degrees, when this warning came out recently, one of the strongest message that came out from me is that we have to reduce greenhouse gas emissions by somewhere between 6 and 18%, depending on who you listen to and how you calculate it. But the crucial part about that, we go, okay, good, we'll do that, shall we? Let's get on with that. But the crucial part of that is that greenhouse gas emissions are completely locked into fossil fuel use, which is completely locked into GDP. So you know how everyone gets upset if growth drops from 3% to 2%? Growth, we have to go minus. Imagine minus 6% GDP. What government is going to be able to sell that one to people? What's that going to look like? I mean, part of the problem is that GDP is such a gross, and it's been renamed, I just wanted to remind people and hope you all use it, it's gross deceptive product, or deception, so we've got to stop deceiving ourselves with GDP. But this is the scary part, and this is the hard sell bit that we've got to get across to people. Look out, there's a whole bunch of countries and some trajectories there you won't be able to see, but locked in GDP and anywhere where you look where people think they're uncoupling GDP from, or that fossil fuel use is declining, or greenhouse gas emissions are declining, but the GDP is going up still. It's only because they've sold the problem to somewhere else. It's just going on some other country. You're getting your cars from somewhere else, and the embedded greenhouse gases on those cars belong to those countries, and you kid yourself because you bring them here that they're not yours. And people really don't understand energy. I've really noticed this as this shocking misuse of electricity and energy and interuse of that. So when New Zealanders say, oh, we're great, we've got 80% renewable energy. No, we don't. We have 80% renewable electricity, which is about 20% of our energy use if you count the embedded energy. So it's 80% of 20%. The rest of it is fossil fuels. So this little example, and this is a lot of fun. You can have a look at this on YouTube. This guy here is a track cyclist. He's like this muscly machine. You've never seen anything like it. What he's got is a exocycle thing there hooked up to a toaster. He's going to toast a little piece of toast in that little toaster there. So if you're ever at the gym on a rowing machine or a running thing or a bike thing, switch it to watts, and you'll see that you go flat out, you can just do 100 watts. Well, I can, maybe if I really push it a bit over. This guy's doing 697 watts. That's almost a horsepower he's doing. And he goes nuts and sweat's pouring off him. And then when he falls off the bike, knackered, they open up the toaster and the piece of toast is barely toasted. And we stick a piece of toast in and we turn the lights on and we start up the oven and all of that kind of stuff with no idea how, and people think, oh, we'll just, stick up a solar panel and we'll be able to power the house. And anyone who's tried that realises that it doesn't work like that at all. So we need to understand just how profligate we've been. You probably can't make out that picture there, but they're actually all people. This is the slaves, this idea of human slaves, which is our energy slaves. Just think about, and I just can't understand why this doesn't get talked about by economists at all, but 1 barrel of oil, and whatever the price is, $65, $70 for a barrel, to give you an idea of how much energy is in that barrel, it's about 4.5 years of work for a human in 1 barrel of oil. So you can buy a slave for 4.5 years for $75. It works out to about, I don't know, what was it? I worked out a cent an hour, less than 1 cent an hour we pay our slaves. And we all have, and this is an American one, but from what I can tell, it's not that much different here, and it depends how you walk it out. But somewhere around 150 to 200 slaves every one of us has working for us full time. You don't have to feed them or house them or anything. They don't ask anything. They're cheap as chips. We're so used to having these slaves. the roads, the cars, everything that makes our lives easy comes from these slaves. And yet they're not, economists don't build this reality in, because when these slaves are gone, who's going to do that work? Okay, so as an ecologist, this is how, so you might be thinking, how does a freshwater ecologist or an ecologist get onto energy stuff? My work, I was working on native fish in New Zealand and about migrating native fish, which is what our fish do, go to and from the sea. A whole lot of them do that at different life stages. Why would they do that? What's in it for them? It's all about energy return on investment. Is that when you work it out, it's worth going down to the sea and living there for 6 months and swimming all the way back up that river again, because it's you get 14 units of energy from the extra food down in the estuary and the ocean for every unit of energy you expend getting down there. This is energy return on investment. This is what, and ecologists call it fitness. Darwin called it fitness, but it's about that ability to be able to get more energy than what you put in the first place. And that's exactly the way we need to look at oil as well. So how much energy do you need to put in? How many barrels of oil to get the barrel, what's that relationship? So when we first discovered oil, I don't know how many of you are as old as me and can remember that movie where Jed Clampett goes out and, the Beverly Hillbillies, and he fires a gun to shoot something and oil spurts up out of the ground. Well, it was like that. It was like that off Taranaki at one stage. That is 100. That's an EROI of 100. It takes you 1 barrel of oil to get 100 barrels. Over time, that number's been going down and down and down. You have to put more and more effort in to get the same amount of fuel out of the ground. If you, think about an apple tree or something like that. The easy bits that you can grab, the close to hand ones, then you have to start climbing the tree to get them, and it gets harder and harder. So the low-hanging fruit is what we had first. Now we're getting into the hard stuff. We have to go into oceans, we have to frack, we have to do all these other things. Plus, along that process of it coming out of the ground. So you start off with 100 megajoules there, but at each process, as you're processing it, you're refining it, you're getting in tankers and taking it to the car, to the garage to be able to use, you end up with 20 units of energy. You started off with 100, you only get 20 at the end as well, so there's that cost of energy in the process. What it means for economies is, this is going back to 1949, when the energy return on investment was much higher. And all you need to do to take, it's just that there's a skinny arrow here for how much energy you need to put in to get it, and a big fat arrow here is the discretionary spending, the spare. By the time you've paid for everything and done everything to get that energy, then there's a big fat arrow of discretionary money that comes out of it. Here's 2030 here. The arrow's a lot smaller because there's this much bigger amount of energy going back to get the energy. So where we are now, we're down to about 14. So it takes 1 barrel of oil now to get 14 barrel, 1 to 14. And then by 2050, when it's like this, see how this discretionary arrow's almost zero, because if you want to have the same amount of energy, you have to put so much more into it, and you get a really sharp decline when you do that. This is what it looks like. Here's where we are, 14. So it doesn't change much, and then suddenly when you get below 14, this is what we call a Seneca cliff. It drops off really, really quick, because to get the same amount there, you need a huge amount, because so much has to go into getting it again. I don't know, it's like if you have to drive 600 k's to fill up your car, you're not going to do it, because it's going to, by the time you fill up the car, get home again, it's empty again. You're not going to do it. That's what happens when you get to that point. As the garage gets further and further away, it becomes more and more impossible. And price doesn't matter. It doesn't matter how cheap or expensive it is, because you had to drive all that way to get it and you don't get anything out of it. So here's a touch of reality about along this. This is how much is available. So how wide these bubbles are is how much is available. And it doesn't matter how much is available if it costs too much to get it, too much energy to get it. On this axis, so here's oil back in 1930, when 100 to 1 when it came out of the ground. This is it in 1970. This is it now. The EROI is dropping really, really fast. And so on the scale is EROI. Hydro goes from 40 to 20, depending on where it is and how hard it is to get. And so as you get, and see those little, that's photovoltaic and biofuels and things like that, they're almost off the graph. They're so tiny. They virtually give you nothing back. By the time you put all the energy into the photovoltaic panels and they have a short lifetime, in biofuels, just not even bother. Don't bother, because you'll put just as much energy into growing the stuff as you will get back out of again. You might as well just shortcut the whole process and save the paddocks for something else and just use the fossil fuels because there's nothing in it. And the reality of this, and this is sort of like a hierarchy of needs here. So at 1.1, and I won't go through this, Charlie Hall's written it all up, but if you only get one for one, you can get it out of the ground and you can't do anything with it. By the time you get up to 3, you can transport it, but then you still have to build the cars and the roads and all that kind of stuff. You can need at least 7 to support a community. You need 9 to pay for some education. You need 11 to have hospitals and things like that, and then at least 14 to get the fancy things we like, which is like arts and sports and all that kind of thing. So this is the reality of our future. And I need to point out that it's also related to wars and terrorism and all that kind of thing. You can follow this in countries where they start to run out of cheap energy, then their economies start to collapse, you get many, many unemployed young people, and you start getting really big problems. Okay, so this is, a lot of people believe we're going to have this lovely kind of renewable future, and I want to just talk about some of the realities of this renewable energy future. A lot of people, and it's so easy to sell it to people. Oh yes, we'll just keep doing what we do, but we'll have renewables instead of this. But there's a reality around the density of how much power is in a handful of fuel, of different fuels. So here's what we need for transport inside this pink thing, and here's all the jet fuel and the gasoline and the stuff, diesel and all these things we have in the car, in our running our transport at the moment. This is megajoules per litre, so this is per liquid amount, and this is per kilogram, per weight here. See these things? And this is how you fly planes and all that kind of thing. You come down to ethanol, then you come down to wood, liquid hydrogen out here. Look where batteries and CNG and natural gas are. They're right on the bottom here. There's not much energy. You need a lot of stuff, and there's not much energy in it. So you can't have battery trucks that drive big distances. You can't have battery cars, as we find, except to shift a few. You can have battery planes to fly 1 or 2 people, but not hundreds of people like we do at the moment. This is the reality that fossil fuels, there's nothing like it for energy intensity. And when they're gone, we don't have any of those things as options anymore. And so this idea that we're shifting towards a renewable energy future, forget it. We have less renewable energy than we had last year or the year before or 100 years ago. We're not cutting back on energy use or fossil energy use. We're just adding to it. We're just becoming more and more addicted. We're like alcoholics or drug addicts. The more you give us, the more we'll use. We'll come up with ways of using it. So this is the reality. Okay, so just to put it into a currency so that you can understand and think about what this renewable future reality might be. And watts per metre squared is kind of a currency that we can compare with what's happening in the rest of the world. So if you take a country, and you could do it to New Zealand, but I'm going to use UK as an example. You take the size of the country and you take how much energy is used by that country and divide it. You get watts per metre squared. So when you work out the watts per metre squared for the United Kingdom, it's 1.25 watts per metre squared. That's the flow of electricity per area of land. Then you take a mix of renewables. So the best renewables we have at the moment, and a whole combination of them, hydro, solar, wind, biofuels, and you work it out for that latitude. So the thing to think about, just a reminder here too, here's solar photovoltaic. You go to the shop, find a metre square piece of solar panel, they'll tell you it's 100 watts. But the reality is the sun only shines some days and it doesn't shine all day. And so what you actually get out of in the UK is about 4 watts. over time, because it doesn't go all the time, you know. So, but of course you want the power all the time. So when you work that out for that country, guess what it works out at? What you need is 1.25. What that whole mixture of renewables will give you is 1.25. So what that means is you have to cover the whole of your country, of the United Kingdom, with wind farms, hydro, solar panels. There is no land left. You'd have to have solar panels on every building, on every car, on everything to be able to power that country. That's the reality. If you take Singapore, and this is showing some of the countries, if you take Singapore, you need 60 Singapores, you know, because it's such a small island with so many people on. United States, continental USA, you need half. You'd have to cover the half of the entire USA with renewables, and just to power them. That's not taking into account all of the copper and the materials and the concrete for the wind turbines and all of the massive amounts of fossil fuel that would have to go into building that infrastructure. So I just want to get people to think about, there's no magic fix here. There's no magic bullet that we're just going to suddenly go from this. Here's New Zealand out there. We've got plenty of area. So if you're just thinking about space-wise, we could do it, but we're part of a planet, a global planet. Okay, so what I'm saying is there's no bright green future for us. We're not going to transition into a renewable. We need to really think about everything comes from the sun, and to build that infrastructure, to have that, the only way we would do that is to stop right now, end of all international flights, cruise ships, toys, SUVs, all that kind of stuff, and all of the energy we have left goes into building infrastructure. That's the only way we're going to do it. Okay, but just thinking about the future for us, and I think this is the best way of describing it. We've got two things happening. We've got declining EROI, which means less and less fossil fuels available. We have to stop using fossil fuels as well. So it's like a pair of scissors or secateurs. If your finger's in there and getting snipped, it doesn't matter which one of those comes first or is the strongest, because your finger's still going to get cut off, right? It doesn't matter. So this is why we need to realise that we either manage the change and get there under our own, make our own decisions about the future, or if we just carry on like we have been doing and, you know, buy more SUVs every year and build bigger airports and just pretend that it's not happening, then that is the future that we'll end up with. We need to be aware of it. So some of the things that we need to do right away, and this is something that I've been working on, instead of on the back of the packet of everything you buy just being all these facts about nutrition, we need a planetary facts panel. Right? How much carbon went into it? What's the EROI per kilogram of this thing? What's the water? What's the phosphorus? How much land got used? Then we can pick up two products and go, I don't want that one. That's rubbish, you know? That's too hard on the planet. This is one way that we could make that future. So I guess that I can skip all these other slides because I've probably gone under time, because we have them. Tangata whenua of this country and many other the Indigenous people, we can learn so much about how we need to be, and our lifestyles are going to be much more like that than what they are at the moment. And you know, so yeah, I'm not going to be here to tell my grandmother how to suck eggs. I'm here to learn. Thank you.